Welcome to Class 3, Thermodynamics. Today we're going to be covering thermodynamic property tables and phases. A lot of this you may know a little bit about, but we're going to get more familiar with these tables. It's very important that we get good at looking things up in the tables. All right, so we start out with Chapter 2, and these are properties of a pure substance, so we have to kind of like define what a pure substance is. There's a little bit too many words here. The basic gist I'll give to you is that, or what you need to know, the takeaway is, of course, there's lots of substances in the world, and we can't treat every one of them the same. We're going to make some assumptions about and consider things pure substances in this class, and not get into the more difficult types of substances. So here's the definition. A pure substance is one that's homogeneous, right? It's kind of evenly, it's the same like everywhere in it. It doesn't have like discontinuities, that kind of thing. And it has the same chemical composition. And it can be a bunch of different phases, but that chemical composition doesn't change for different phases. So like water is a classic example. It's the one that will probably do the most amount with that, and air. Well, we have the different phases of water, but we also can have mixtures of those phases. Like we can have a mixture of liquid water and water vapor at the same time, aka steam. We can also have like a mixture of ice and liquid water at the same time, and those chemical compositions don't change. But in contrast, you could have like liquid air and gaseous air, and they might change because you could have nitrogen and oxygen and then a couple other gases, but that's basically what you have in air, and those aren't necessarily the same. But we can treat them like a pure substance because that's going to be very useful to us. So we probably won't be looking into the really cold air and using that for any practical purpose, but within the boundaries of sensible ranges of temperature, we will treat air like a pure substance. I think that's all we had to say in there, right? We can switch over to the note sheets and take a look at some further definitions, where we're talking. First, we have saturation temperature, and saturation temperature is basically the same thing as the boiling point, right? So this is the temperature at vaporization. So it's the phase change from the liquid to the gaseous state. And I wrote AKA this way on my notes, so kind of like that. Right? We also have the freezing point, and I wrote ice, ice, baby, because that was funny, I guess, before. See, that's this thing right here, by the way. Okay, so this is the, that said baby. It didn't look like it said baby. And so the change of phase again. So now we have something called the triple point, and this is an interesting one where all of the phases exist all together, right? All phases exist together. This is probably a difficult one to actually achieve, but what we want to take a look at is this little graph down here. This is figure 2.2 from the textbook, and you can see that we have solids, liquids, and vapors. And if we go back up to this little experiment here, we can try to adjust this. We could take we can, I guess, remove the weights. I was thinking of replacing the weights, and we can remove the weights, and for whatever method we're trying to get, we can get the water vapor and the liquid to exist at the same time and keep removing the weights. So we're changing the pressure. So something I lacked, I should have pointed out up here, right here. It's the temperature at a particular pressure. Right? So pressure and temperature, both of them matter. Should have put this up there. Particular pressure, both of them matter to establish what this state is going to be. And so we could see that this combination of pressures and temperatures, we could vary them and take data where we see we're just on the verge of being a solid or just on the verge of being a liquid, and we could change what that temperature is. You can bring the pressure down, and then you can see you can do the same thing over here for a liquid and a vapor. We can keep changing and changing, and we'll eventually see that we'll have these boundaries, and right here exists the triple point. So these often these will have a particular name, and we can call this like a phase diagram. We have the solid and the liquid and the vapor, and here's our triple point right here. And there's even a critical point right up here where we don't have like it stops behaving with the stuff that's in the middle, right? So sometimes there's going to be like this combination phase where we have both liquid and partially liquid and partially vapor happening at the same time, but if a critical point above that, we have instantaneously, we change from one phase to another phase. Some of these things, these are on the extremes, and we don't necessarily cover them. The critical point, let's see, okay, here's the definition I wrote down here, was the pressure above which heating produces vapor without boiling, right? And so an interesting and important thing that we will see off of diagrams, so be on the lookout. Here's a little bolo. During this thing where we're going from liquid to completely vapor, there is this combination of liquid or vapor and liquid existing at the same time. But be on the lookout for when that happens, because interestingly, the temperature remains the same. Bad handwriting. During vaporization. And we'll notice that. Now, so we've just started talking about graphs. And graphs are really important to us in thermodynamics to try to look up the properties based on two properties most of the time, right? So this is, sometimes you need three properties, but most of the time you only need two properties to be able to completely define, say, like water. What it's doing when it's but quite often we often will need three, because that third one might be the percentage of vapor within that mixture of vapor and water. So let's take a look. I have through what is these PVT diagrams, which I have put together right here, just sort of a walk by walk, right? So there's a lot going on here. But and you might want to walk through this several times to try to become comfortable with it, so more familiar with it, with these diagrams. All of them you want to become very intimately familiar with. So we're going to start off with A and B right here. So you can see they have temperature and volume. And by the way, there's a lot of different graphs, but quite often temperature, volume, and pressure will be ones that we will see in some kind of combination. There's some other graphs that we're going to take a look at, but these are combinations that we will look at quite often. And if we go from A to B, right, so first off, what they're showing, make sure we label this, atmospheric pressure is 0.1 megapascals. So we're temperature versus volume, and we can say at point A is room temperature liquid water, right there. And if we come up to B, right in here, I was going to make some animations on this and I didn't. We could call that saturated liquid, right? So they're saying that's 96.6 degrees Celsius, which means it's about to start boiling, right? And then as we move from B to C, and this is going to like up hot on your stove because it's atmospheric pressure, we will see that the temperature remains the same, and we're going to have increasingly amount of vapor, percentage of vapor here until it gets all the way up to here. So this will be 100, or they're saying 96.6. They're being very specific. I'm not sure why they have to be so pedantic, but it's okay. 100 degrees Celsius right in here across all the way until it gets all the way over there. And we call, by the way, between B and C, we call that wet steam. Now we get over here, and now we've dried the steam out. We have the saturation vapor, and now the temperature will start going back up again. It remained at 100 degrees Celsius all the way along here, and now it'll start moving up here. And now we consider this zone up above, over to the right of this dome, we consider that to be superheated steam. And that's an important term, and with a few exceptions, for most steam plants, when we want to use superheated steam inside a turbine. We can't do that, interestingly enough, in a nuclear power plant. I could explain that some other time. All right, so now if we go up at higher pressure, let's go up to 1 megapascal, right? So 10 times the atmospheric pressure. So that's right up here. And we start at E. Now this is a pressurized liquid, right? So we might be in a pump. It might be constrained inside a pipe, you can think of, that we've just pumped it up. And that could be true in a boiler, right? Because we could have the pump has to have a higher pressure of water than the steam or whatever is inside the boiler, or the hot water in the boiler, because the pressure always drops across things except for a pump, obviously. So we move up to F, right? So we went from E to F up here. And once again, so this particular one, we notice that they're saying that correlates to 180 degrees Celsius. Now we could find that, we could look that up in the tables in the book, and we will probably in the next video, because this one has already gone up to 11 minutes. So 180 degrees, and now we have this mixture up here between F and G at 1 megapascal, or is that I don't know, is that 1,000 kilopascals? Yeah, I guess it is. We get in between here, and once again, this is wet steam, and if we want to find a property, we need to know how much how wet the steam is. And then we get over here to saturated steam, so now it's completely, we can say that we've just dried out the steam, and now we're going to superheat it again. And this, by the way, these are lines of constant pressure. And they didn't have to be lines of constant pressure, but that's just it for this demonstration. That's what we're going to hold as a constant for all of these lines. And then we have way high pressure, so we went to 10 megapascals, so that's 100 times atmospheric pressure, which is pretty significant. And so that's up here, and we can see that we have I. It's going to go I, J, K, and L. So we're going to do the same thing. Come up to here, come across, and then come up. And then we have ridiculously high pressure, 22 megapascals. And we're not even getting in, we're going from liquid right here, pretty much at the critical point. We're going boom, right up to steam. So we never go to wet steam. And then, so we no longer have a liquid vapor mix. And then ludicrously high, they're saying 40 megapascals. I don't know if that's possible, but probably is somehow. It's a mystery because that's like 5,800 psi, and that's just like a crazy amount. But that's like what researchers look for and stuff, and we don't really care about what's taking place right in here. So here's my, sometimes we call this like the vapor dome. This little dome, and we can take a look at it from various vantage points, like here from the left and here from the right. So take a look at the axes. We have the pressure, the volume, and the temperature, and those are our main kinds of. And by the way, these is specific volume. We probably always just assume, right? Because we don't really care about the actual volume. We care about really kind of the inverse of the density. And they can be kind of a little complicated, and there's lots of details to be seen inside these. I don't expect you to know every single part of these, but this is just mapping out how nature works, right? So these were taken with, in a laboratory and found to be repeatable. And of course, when you coming back over to this page right here, what I do with it. There's a really important type of idea as an engineer, that these weren't magical points. They're actually points that are like this right here, like all over the place. And because when you run an experiment, the chances of you getting the same number twice are nearly impossible. You get close if you're running your experiment very, 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 very carefully. You can get very close, but you're still going to have a cloud of data to make. So keep that in mind when we take a look at like any of these tables and any of these graphs, that they were, people took a high amount of precision on top of them, but they still didn't have some kind of like, perfect lines that always landed on top of each other. They were repeatable by other people in other locations, but they too were going to be ever so slightly off. So, and by the way, this graph right here, that one that you're seeing, is from this side right here. You're looking from that direction at the thing, so you can kind of see where that point is that we're put on here, and where that critical point is, and you can also see where the triple point is located way down into there. I think that's long enough for 15 minutes. That's a long enough video. We're going to take a look at some tables in the next video. We're going to get very familiar with these tables. That's why you need to bring your book, probably to class. Maybe I should send an email, say, bring your book to class. Bring your book for exams. It's going to be open book test, but you're going to need to know how to what's in these tables and how to look them up. And you need practice in order to do that. So we'll talk in the next video.